Okay, so this chapter is more panic and phantoms. What is different with this chapter compared to what we've done previously is we're going to be looking at two populations. So we're going to look at two samples, and then we are going to construct a confidence interval or carry out a hypothesis test with those two samples. So we will be learning 3 new confidence intervals, 3 new hypothesis tests. The procedure mostly stays the same, and a lot of the assumptions are the same. What changes is the formulas. So today, we are going to look at mean, and we will carry out an entire hypothesis test, and then I will just tell you what the formula is for the confidence interval. You are going to have a quiz after section 2, which is March 8th. It's on Schoology. And then your test over this chapter will be right before spring break. So it's either going to be that Monday or that Wednesday before spring break. Sound good? Okay, great. If we look at the first page, this is the data that we are looking at and the context. So like I said, we're just going to jump right into a hypothesis test. A 1975 experiment attempted to modify the weather. The following information is from the original study. Clouds were randomly seeded or not with silver nitrate. Rainfall amounts were recorded from the clouds. The purpose of the experiment was to determine if cloud seeding increases rainfall. So then you're given the data. So the rainfall from the cloud seeding, the rainfall in acre feet from 52 clouds, 26 of which were chosen at random and seeded with silver nitrate. Okay, before I keep going, do we understand the context and the data that we are looking at? Hello. Thank you for you 3 nodding at me. Over here. With me. We had 52 clouds broken up into 2 groups, 26, 26. 26 were unseeded, 26 were seeded. And then we looked at rainfall after a certain amount of time. Okay, so then that is the raw data at the top. So I could just give you this information and ask you to carry out a hypothesis test. Or I could give you this information down here, which is the summary statistics. So this is done by Minitab. You'll see we have the 2 variables here, seeded and unseeded, and then we have a whole bunch of information. You're given the mean, you're given the standard deviation, you're given the 5-number summary, and you're given 2 different dot plots. Overall objective, we want to know, did the seeding increase rainfall? Ready to do our hypothesis test? Okay. In this case, we have 2 samples. We have 2 means that we're looking at. The mean amount of rainfall for the seeded clouds and the mean amount of rainfall for the unseeded clouds. So the first difference is that we're going to have 2 parameters to define, mu1 and mu2. So I'm going to say let mu1 be the population mean rainfall for the unseeded clouds. Mu2 then is going to be the population mean rainfall for the seeded clouds. Doesn't matter the order that you do. If you wanted mu1 to be seeded, that's fine. Okay. So then, writing our hypotheses. Both our null and our alternative will be in terms of mu1 and mu2. You have 2 different options for how you can write these. Ultimately, we want to know if the rainfall is higher for the seeded clouds. So the first way that we could write this is we are going to assume that the rainfall is the same for the 2 treatments. And then we want to know, is there evidence that mu2, the rainfall for the seeded clouds, is greater than the unseeded clouds? That is the first way to write the hypotheses. This is also written sometimes like this instead. mu1 minus mu2 equals 0, and mu1 minus mu2 is less than 0. I tend to use the notation in green, but a lot of students find the blue to make more sense. Either one is fine. I will accept either, and College Board will accept either, so pick whatever notation you prefer. Okay, good so far? Great. When we go on to our assumptions, assumptions are going to be exactly the same, for the most part, as if it were one sample for mean. What is the first assumption always? Random. Okay, this is where we need to be very careful with our random. Random has two meanings, if we remember. Is it a random sample, or were the treatments randomized? What is the one in this case? Random sample or randomized treatments?
Randomized treatments.
Randomized treatments, and why?
Because the samples are chosen.
It's an experiment. Yeah, it's an experiment. So you need to be specific with that. Were the treatments randomized? Do not write random sample question mark or random question mark. Instead, we want to know, were the treatments randomized? And we're going to say yes, stated. Second assumption for mean.
Sample is less than 10% of the population.
Okay, 10% rule. Last one. Normal sampling distribution. This is a little bit more work because you actually have to check for both samples, for mu1 and mu2. So we are not told the population's normal. We can't use the central limit theorem because our sample sizes were 26. Don't construct a graph. You already have a graph. You have the two different dot plots. Do they show extreme skewness or outliers?
Yeah.
A little bit of skewness.
An outlier.
And maybe an outlier. Okay, we're just going to assume that the sampling distributions are normal then. So I'm going to say, because the distributions of the samples show skewness, we are going to assume both sampling distributions are approximately normal and we will proceed with caution. So this assumption needs to be checked for both. I will tell you, I'm going to be very picky that you use plural to show me that you are talking about both sampling distributions. So if you say something like, the sample does not show extreme skewness or outliers, the sampling distribution is normal, I'm not going to take that because that does not indicate to me that you looked at both distributions. The 10% rule is not necessary in this case, and why is that? There was no sampling done. We can assume that these clouds were volunteer clouds. We didn't take a sample of clouds. Okay. So these are in the case where it's an experiment. If you have a survey instead, where it's not a sample, here's how things change. You would need random samples. So both samples would need to be chosen randomly. You would still need the approximately normal sampling distributions. There is one new assumption. This assumption does not apply if it's an experiment, but it does if it's a survey. If it's a survey or an observational study, your samples need to be independent. So how one sample was chosen needs to be independent of how the second sample was chosen. Again, that only applies if sampling is done. So if you have a survey or an observational study. And then lastly, here is where we would need to check the 10% rule because sampling was done. Because we have two different samples, you have to check the 10% rule for both. So your first sample would have to be less than 10% of that population. And then your second sample would have to be less than 10% of that population. So every assumption that you're checking for both samples. So it's a little bit like there's double work. So this one I think is a little bit tougher because the assumptions change a little bit depending on if you have an experiment versus a survey or an observational study. Questions on those? On the assumptions? Okay. For N, this should be pretty intuitive. This is a two-sample hypothesis test. For mean. This is lower-tailed. Alpha is 0.05. And we are using T. Same as before, if I gave us a population standard deviation, you would use Z, which is pretty much never. So if we're using a sample standard deviation, it's going to be T. Here's how you figure out degrees of freedom. You do N minus 1 for both samples, but choose the smaller number. So we have 26 clouds, N minus 1, 25, 25. So in that case, doesn't matter. We're going to use 25 degrees of freedom. So again, N minus 1 for both samples, choose the smaller number though. Okay, questions so far? Okay. So then moving on to our test statistic. Things are gonna get a smidge bit hairy here. Can you take out your formula sheets, please? Okay, so I wanted to show you or wanted you to take out the formula sheet so that you can figure out where this formula comes from. On the front page at the bottom, or near the bottom, it says standardized test statistic, that's our T, and it tells us in words what the formula is. Statistic minus parameter over standard error of the statistic. Parameter is the null. So if we look back at our null, if we look back at our null, I'm not going to pull it up, but it ends up being mu1 minus mu2. That's our null. Parameter comes from a population. So then the statistic, the sample statistic that goes along with that is x1 bar minus x2 bar. The standard error is going to be on the back page. So if you flip over your formula sheet, the top is proportions, which is not what we want. The next section is means. We are looking at two populations. So then it says standard error, and that's this formula right here. This formula right here. So it's going to be the square root of s1 squared over n1 plus s2 squared over n2. So that is on your formula sheet. If you can connect the dots a little bit, you should be able to figure out the formula without having to memorize it. Okay. I believe, just to remind myself, that sample 1 was unseeded. Is that true? And sample 2 was seeded. Okay, so if we look back at the previous page, I'm not going to pull it up because it's going to mess up our recording. We need to find x1 bar. So that is the sample mean for the unseeded clouds, which I believe is 164.6. Do you all see that in the output? So in the output, you should see that the sample mean for the unseeded clouds is 164.6. For the seeded clouds, it's 442. So then this mu1 minus mu2, what comes from the null, that is our assumed difference. We are assuming the difference is 0. So then that S1, make sure in the output you're using standard deviation. Standard deviation. So we have 278.4. This is 278.4 squared over 26. And the other one is 651 squared over 26. Take a minute, put this in your calculator, and see if you can come up with the test statistic, please. Okay, we're not going to calculate our p-value just yet. We're going to draw our figure. So, of course, we're going to put our double labels. This 0, our assumed value, will go down here. So you're actually going to have a double 0. And then the standard deviation is everything that's in the denominator. So this entire value right here ends up being about 139, let's say. That's what goes on your figure then. So one standard deviation above would be about 139, and then about 278. Negative 139, negative 278. So then our test statistic is about -2. We said it's a lower tailed test, so we would shade below that. The value that goes along with that -2, the contextual value, is this. That 164.6 minus 442, that's the other label that would go here. Now, practically, a lot of you have not been doing that. As long as you have one of these two labels on the figure, that's fine with me. So if you just want to label the test statistic and you don't want to label x1 bar minus x2 bar, that's fine. So then we are finding the probability that t is less than or equal to -2. On your calculator, as a reminder, you're going to do TCDF. Lower bound, upper bound, degrees of freedom. So, do that now, please. And you should get about 0.028. Do we? Okay, so then making our decision, that value is less than 0.05, so we're going to reject the null. And then we're going to write our conclusion. I do want us to write a conclusion together just to make sure that we get the right wording of things. So, based on my analysis, I reject the null. And instead believe. Okay, I'm going to talk, then I'm going to write. Our alternative was mu1 is less than mu2. So we need to put that into words. Mu2 is the seeded clouds, mu1 is the unseeded clouds. So I'm going to instead believe that the population mean rainfall for the seeded clouds is higher than for the unseeded clouds. So I just put in words, mu2 is greater than mu1. Mu2 was rainfall for the seeded clouds, greater than for the unseeded clouds. So that is the first sentence. We need to interpret our p-value as well. So 0.028 is the probability of obtaining. Okay, in this case, our statistic, it's the red that I circled in the formula. It's difference in sample means. So it's the probability of obtaining a difference in sample means of, that difference was negative 277.4 or smaller if the difference in population mean rainfall amounts is 0. And that's what we assumed. We assumed that there was no difference in the rainfall amounts, and then we looked for evidence to the alternative, or to prove otherwise. We are not finished. Why are we not finished? We didn't answer the question. The question asked, did it appear that seeding increased rainfall? So, does it appear that the seeding increased rainfall? Okay, are we able to conclude cause and effect? Seeding increased rainfall? Are we just automatically assuming I'm looking for a no because you keep shaking your head no? When are we allowed to show cause and effect? It's an experiment. Was this an experiment? Yeah, definitely was. We randomized the treatments. So yes, it appears that the seeding increased rainfall. Who or what does that conclusion apply to? This cause and effect conclusion? These clouds or?
Clouds like it.
Yeah, these clouds or clouds like them. I don't know what that means practically, but these clouds or clouds like them. So my caution to you, just as a reminder that I think we know, just because there is a correlation between two variables does not mean that there is a causal relationship. So just remember, like we said, you can only show causation if you have an experiment, and then it only applies, or you can only generalize from that experiment if it was a random sample. Like I said, I'm assuming these clouds volunteered, so they do not constitute a random sample. Besides the formula, and this being slightly more work, it should remind you a lot of what we've already done. Okay, if you go to the next page, I want to show you a little bit of some different output. So this is some other output that you could see. It gives us just the information that is most important to us. And this is one where the test was actually carried out for you. So occasionally on the AP test, you're not going to have to carry out the test. You're just going to be given the output and asked to make a conclusion. So what you need to be able to find in this output is, first of all, this is how the parameters were defined. So unseated versus seated, which is what we did also. And then the estimate for the difference, that number should look familiar to you. That is x1 bar minus x2 bar. And then it tells you what test was done. So it was a lower-tailed test. It shows you the test statistic and the p-value. What I do want you to notice is that there are degrees of freedom, and those degrees of freedom are different than what we used. Here's why that is. There is a complicated degrees of freedom formula that is technically the correct way to do this test. We will not use that formula, though. So we use what's called a conservative estimate. So that's the sample size minus 1 for both samples, and choose the smaller one. That's conservative. So just know that on the output and on the calculator, the degrees of freedom are going to be slightly different. You with me? Okay. For a confidence interval, here's the formula. Again, on your formula sheet, it's in words. We just have to be able to put it into symbols. So it starts with statistic, which we've done. That's the x1 bar minus x2 bar. Plus or minus. Here's the one that students have trouble with, critical value. Critical value is just t or z. So in our case, it's going to be t. And then it's the standard error again. And it's going to be a similar idea. You're going to need to define both mu1 and mu2. You're going to have to check the assumptions for both samples, not just one. And those will be different a little bit depending on if it's an observational study versus an experiment. Questions on that formula before we look at all the things on the calculator?